All right, this is the spectral lines simulation worksheet, neon lights and other discharge lamps PET simulation. And in case you don't have a computer available to run the simulation, that's what you're watching here. So the manipulations that you're requested to perform in the Unit 2 activity, again, we're investigating relationships between frequency, wavelength, and energy of emitted photons of light and what that has to do with the atom structure, atomic structure. And so again, the beginning says just to kind of investigate what exactly we're looking at here. So I notice we do have a voltage set. We can fire one electron at a time. We can do continuous. We're going to do continuous to save my fingers from clicking. Notice that we can increase our rate of electron production. And notice the numbers appearing as these photons hit this. So just kind of take a look at this whole scenario. There's a spectrometer. I'm going to run this in slow motion just so you can kind of see what's going on. So notice the relationship between the numbers over here and over here on the right-hand side. So notice the electrons are coming through and continuing on, but these are supposed to be photons of light. Adjust the voltage. Notice what the voltage change did. It's changing this over here. So there's actually, because of this voltage, it's pulling the electrons from this side to this side. And so that's kind of the difference. And also that changed the energy at collision. Watch this also. So notice what effect this has. Now, obviously, if I move this out of the stream of the electrons, we're not going to get anything going on. Multiple atoms. Back to one atom. So this, with what you're observing right now, should be able to answer your first question. Describe what happens in a step-by-step fashion. Notice this over here. We've already investigated the second question. Notice what's happening down here also. I'm going to put this on continuous and speed this up a little bit. Notice when we see the different colors of squiggles on the down, we notice they're adding to the count on here. Okay, so this is showing me anytime a purple squiggle or a bright blue squiggle or a red squiggle come out, that's kind of being tallied here with these lines. So that's something to note. All right, so we should be able to answer the questions on the first page, 1 through 3. What role does energy play in the production of electromagnetic waves? Well, that's for you to kind of think about and write down. Should be able to answer 5. And 6. Feel free to rewind and replay. But again, if you're trying to answer question 6, take a look at where the electron is bouncing between. So it goes up and down. Notice when it stops at different levels. Okay, so for part 2, we are going to go to the Multiple Atoms tab. And we're going to start with hydrogen. And we're going to put on the spectrometer. So we're drawing where these lines, colored lines, are appearing on the wavelength spectrum that you have on your paper. So you're drawing those on. You can write down which color they are, but obviously whichever wavelength they are, that kind of tells us the color. We can compare it to the spectrum. And we just need to do the visible ones, so you don't need to do these ones over to the sides. Those are in the UV and IR range. So just in this 300 to 800 range, draw these lines. Okay, so that's hydrogen. We are going to do mercury next. There that is. I'll amp up our production here. Go faster. So there, you can see your colors coming out. Document those. Oh, another one coming here. All right, we'll do sodium next. Again, these will just keep going if I let it keep going. So, sodium. And neon. Okay, so for your next questions, so these lines are still filling in for the neon, but this is based on your observations using this model, which colors of visible light are highest in energy. So we're justifying with things that we've observed in this simulation. So I'm actually going to do some manipulations here to help us make sure that we have proof that we can cite to make our statement. So I'm going to go back to one atom. I think we've got enough for these lines for sodium, or sorry, for neon. There's another one coming up right here, but all right, let's go back to one atom. And I'm going to do configurable. So I'm going to put in a couple of levels here. So notice the color changes between these different drops. You keep seeing the green light come out. I'm going to actually shift these around a little bit. Oh, notice when I moved 4 closer to 5. So, let's kind of see what happens. So notice the differences in the colors when we're going. You see this electron jumping from, so this is the electron jumping from one energy level to another. So look at the colors that are associated with the bigger energy jumps. So like when I went from here to here, I'm going to shift these around. So I put these two closer in energy. I got the green color. And I made these a bigger difference between them. Notice when we went from 4 to 3, we got like a reddish color. Oh, there's yellow. And so how can we, and I know we talked about this in class, how can we use what we're seeing here to confirm what we're saying. There was just a big purple jump, so rewind if you need to. So there was a yellow from here to here, there's a purple from here to here. How can we use those observations to answer question 1? In part 2, that is. Right. Okay, so for part 3, we're going to start producing electrons to use a simulation to gather information and answer the following questions. So we're going to select the 1 atom tab, which we're already there. And in Bohr's model, the hydrogen atom principal quantum number n increases, energy levels follow a clear pattern and converge. Identical pattern is found for mercury, neon, and sodium. So let us try that out. So there's hydrogen. I'm going to run this faster. So there's hydrogen. There's mercury to compare. So notice the difference in energy levels this question's asking about. Sodium. And neon. Alright, should be able to answer number 2. Energy emitted from the discharge lamp is quantized. So true or false based on what you see on the spectrometer. And then I guess looking back at what we saw over here, here's your evidence. Should be able to answer 3 with what we've seen so far. Again, feel free to rewind anything to take another look. Alright, to answer number 4, let us do we'll do a configurable. There we go. It says the line spacing between 2 electronic energy levels in atom A is larger than in atom B, then the wavelength of light emitted by atom B will be longer. Okay, so I'm going to just take myself down to 2 levels here, just to kind of see. Dial this back a notch. There you go. Okay, so 2 electronic energy levels in atom A, the spacing is larger than atom B. Okay, so let's pretend this is atom A. And so this is the larger spacing. And let's make atom B, we'll put the spacing like this. Let's try this again. So let's make this atom A. We'll make this atom B. Right. Kind of use this to answer number 5 as well. Spacing between 2 electronic energy levels in atom A is smaller than in atom B. So you're going to have fewer photons emitted. Let's pretend this is atom A. And let's pretend this is atom B. And for 6, I think looking over here can help you answer that question. All right, the next section has us looking at the emission spectra for single atoms of hydrogen, mercury, or sodium. Actually, we're looking at for neon. So single atom of neon is what we're supposed to be doing here. The last part here. There's a single atom of neon. It says try to manipulate the different variables: voltage, number of electrons produced. Okay, so there's my number of electrons. Okay, about voltage. Crank that up. So again, notice the changes that I made to voltage and the positioning of my atom, what that does to over here. All right, I think you got enough to answer your questions. Oh, the next section, multiple atom tab. There's energy levels very close to the ground level state, so that should help us answer number 2. Notice this when I move these down closer. Just another look at mercury. Look at sodium again. Should be able to answer the remaining questions with what you're observing here. Again, feel free to rewind back to any point. And I think that should get you through the simulation if you didn't have access to it yourself.